Bom dia, desculpa, boa tarde. O Henrique, que organiza os colóquios, hoje é aniversário dele, então eu vou fazer a apresentação da nossa palestrante de hoje. A professora Geetha é da Universidade de Warwick, ela está aqui no CBPF numa colaboração comigo para síntese de materiais monocristalinos, e hoje ela vai falar, então, de materiais Skyrmions. A formação dela é em física, ela fez toda a graduação e pós-graduação na Índia e toda a vida profissional na Inglaterra, na Universidade de Warwick. Então, a apresentação vai ser em inglês. And we welcome Geetha.
So, thank you very much for the very kind invitation. I'm really pleased to be here. It's a lovely place. This is my first visit to Brazil, so my Portuguese is not really up to anything. Given that this is quite a new topic that I'm working on and would like to speak to you about, I think I'd prefer to stick to English. So, I gave several options for the talk to Eduardo, and he suggested that there may be some interest in this area here. Like I said, we've been working on this project only for a short time now, so it's been quite a learning curve for me. So I'm by no means an expert in this field. So at the outset, I want to say that I'm an experimentalist, so the talk will be focused around materials that exhibit skyrmions. Now, as you've heard, I'm from the University of Warwick, which is in the UK in England. And for those of you who don't know where the university is, so we are in the middle of England, and basically that's called the Midlands. So we are only about 100 miles from London. So it's about an hour by the fast train. The closest airport to us is Birmingham International Airport, which is just 20 minutes by train or car. And for those of you who have read Shakespeare, which I think most of you have heard of Shakespeare, we are very close to where Shakespeare was born, the historic Stratford-upon-Avon birthplace of Shakespeare. So if there's one thing that most undergraduates take away from my talk when I go abroad is that the University of Warwick is not in Warwick. So they're always very amused by that, by the fact. So the University of Warwick is actually at the edge of Coventry, so it's in the green belt in Coventry. The university actually straddles the city of Coventry and the county of Warwickshire. So there's a road that goes through the campus that divides the two counties, and therefore students on one side, living on one side of the road, would vote in for a different constituency, so they have a different member of parliament to students who live on the other side of this road that divides the campus. And Warwick itself has a lovely historic castle which dates back to the 12th century, and it's still very well preserved, and that's one of the highlights of anybody's visit to the university, apart from the research, of course. So that's our department, the building. So that's sort of where the university is and where I've traveled from to get here. The university, I just want to give a few facts about the university to set it in context with other places here. For example, we are a very modern university compared to other old British universities. We are just over 50 years old. Around 1965, there were several universities that were built in the UK, and Warwick was one of them. So the city of Coventry was chosen to house this university. So it started off as a very small place with just 450 students. And the first vice chancellor was called Jack Butterworth. And then in 2017 now, we've got a total student population of over 20,000, of which we've got about 13,000 undergraduates. And all the first-year undergraduates live on campus, so there's about 4,000 to 5,000 of the undergraduates alone living on campus. So there's campus accommodation to house this many students, as well as some postgraduates in their first year. So we have about 30,000 undergraduate applicants applying to the university, of which around 4,000 odd are chosen. And the staff as well, as you can see, which is not just academics, this is all of the staff in the university. Yeah, I'm just coming to this. So international students are basically non-UK students, so they could be from the EU as well. So we've got roughly about 30% of our intake is from outside the UK. So these numbers would add up to about 30%. And so we have got alumni living in many countries around the world. And also among the research and teaching staff, you see a very large fraction come from outside the UK. So you can imagine the influence that Brexit is going to have on, in general, the university sector in the UK. We also have a very small representation from Brazil, and these are numbers given from the international office. So we've got a small population of about 35 students, and we even have members of staff who come from here in certain departments. Now, before I came here, I spoke to the international office, or rather the international office in the university spoke to me, and they gave me these figures for their activity in Brazil. I've got more information with me if any of you are interested. So they do have some programs which fund collaborations between the universities here and Warwick, but when we tried to get funding, I found that most of the funding did not come to this state. It went to some other states. So we were not eligible for a lot of the funding that was offered. But we do have some exchange with this university here in this city. So there are undergraduate exchange students. So our students would spend a year here for their undergraduate degree and then come back, and therefore there'd be a mutual sort of exchange. And so this is possible. So so that's about the university in general, and this is about the physics department. So these are the various groups within the physics department, and I'm part of the superconductivity and magnetism group, which is a subgroup within the larger condensed matter physics area. At one point, the condensed matter physics used to be the major research effort within the department, but over the last 15 years, we've expanded to take in groups which work in astronomy, particle physics, astrophysics, and plasma physics as well. So these are the main research efforts within the physics department, and we are roughly about 60 academic members of staff to teach our students and to do research. So just for my own effort there, so as I said, I belong to the superconductivity and magnetism group, and our main source of income is from grants funded by the Research Council. We don't get any money from the university for our own research. We have to bring in all the money externally. The university will match some funding for some equipment, but that's about it. So we have to bring in a fraction of our salaries through these external grants. So for the subject of my talk, the two grants that I hold, which are most relevant, are the single crystal growth at Warwick grant, and then this grant here on the skyrmionics, which is just under a year old now. So we've just been working on it for a few months, and that's what I'll give you an account of, just a little bit. So this Skyrmion project was funded by the Engineering and Physical Sciences Research Council, and this is a national project which has funded 5 different universities, all joined together to work on skyrmions, and I'll explain what the different nodes do and what my responsibility in this project is. So basically, we've broken down the project into various segments as Research Challenge 1, 2, and 3, and I'm really associated with the Challenge 1. So this is what the program looks like. And so these members who are the investigators are named here, and I've tried to put them in the same order as they appear here. So basically, we have an effort at Warwick which concentrates on the materials aspects of the skyrmions. We have Durham University, where they'll investigate the dynamics of skyrmions and understand the physics of skyrmions. And at Oxford, the effort would be to produce thin films of these skyrmions and do some experiments on the thin films. And in Cambridge, the main effort is to study these skyrmionic materials using electron microscopy. So this is Lorentz force microscopy on these materials. And at Southampton, the focus is on modeling and simulation studies. So these are all the people who are the investigators at the various nodes of this project. This project runs for 6 years, so, and they've sunk quite a lot of money into this. So there is a lot of pressure on us to deliver on our stated aims. So one of the main aims is to, for us concentrating on the materials, is to expand the range of materials that exhibit skyrmions, both in the bulk as well as thin films. I won't be talking about thin films because that's not the work that we do at Warwick. The most of the thin film work is to be done in Oxford. I'll talk about the bulk materials that we will be working on. So once the materials are made, then the focus is to study the formation, the stability, and the dynamics of skyrmions. And we'll also be imaging the skyrmions both in the bulk, which is in crystals, as well as in thin film form. And then eventually, as with most funding applications, we have to promise that there will be something at the end in terms of applications. Of course, that is a long time from now, but we have to have that in our minds all the time. So at Warwick, the challenge is to produce the materials. So our aim is not just to produce materials that are well known and well studied for further investigations, but part of our remit is also to try and expand the range of materials. So there is some element of discovering, if you like, some new materials that would be suitable to exhibit skyrmions. So the main people who, apart from me, who will be working on this are the senior postdoc Monica, and the new postdoc Alice, who's been appointed as part of this project. And then Don Paul does some neutron scattering work, and Martin Lees at Warwick does most of the low temperature measurements. Those two are my colleagues. So what I plan to do as in this talk is just to give you a broad introduction to what skyrmionic materials are. I'll tell you about some of the techniques that we use for synthesizing these materials, and give you some examples of the different materials that we are investigating, and then maybe talk about some new projects. So we've been talking about skyrmions for the last 5 minutes or so, but I still haven't introduced what skyrmion is. Now this was the term skyrmion was actually coined by the British scientist Skyrm. So there are very few particles in physics which are named after people. You're probably most familiar with Fermi or Bose or Higgs, and not many people have heard about Skyrm. So Skyrm is actually a British scientist who studied math at Cambridge, and then he also worked with Rudolf Peierls of the Peierls transition during World War II at Birmingham. He later on went to work at the Atomic Energy Research Center in Harwell in the UK, and this is where he first proposed this notion of a skyrmion. Okay, so he's best known for formulating the first topological soliton to model a particle, and that is the skyrmion, and this was done way back in 1962. And he was given the Hughes Medal of the Royal Society in 1985, and he died in 1987. So that's the history of Professor Skyrm. So what is the skyrmion that we are talking about here? So it's a topologically stable and non-trivial spin structure in magnetic materials. So they are particle-like, and they can exist over a length scale, quite a large length scale actually, depending on the material. And then they present themselves as a lattice, very similar to vortices, and I'll tell you how this comes about and how this is detected. So if you take, this is the common image of the skyrmion for those of you who have seen it. So it's like a hedgehog. You've got all these pins pointing out from the sphere. And then the way to view this in a plane is to comb the hairs on this sphere. So this is like a combed sphere, and then project it onto a plane, and that is what you see as a vortex. And this is seen as a lattice in materials that exhibit these excitations. Okay. So these vortex are topologically equivalent, and they are both skyrmions, this object and this object here. So this is the figure that you will see quite often, which denotes what a skyrmion is. Okay. So how does this come about? So you've got magnetic excitations that arise from the interplay of two different types of interactions in the material. So we all know about the short range interaction between spins, which would give rise to alignment of the spins, as in a ferromagnet, for example. And then if you add to this the relativistic spin orbit coupling, and this gives rise to what's called the DM interaction, and this DM interaction usually tends to cant the spins in a material. And so the interplay between these two interactions gives rise to what we have as the skyrmion. So you've got this the spins pointing one way on the outside, and as you go inside you see the spins pointing inwards. So after the prediction of this sort of object, the theoretical prediction of magnetic skyrmions was actually made 40 years after Skyrm, and that came about in this paper here by Bogdanov and co-workers. So it took a long time for this skyrmion to be predicted, and then later on to be actually observed. But what was really exciting about the skyrmions is that you can control them using either electrically or through magnetic field gradients over certain temperature windows. So what happens is, as the electron moves through the skyrmion, the whirlpool that you see there, its spin orientation will be adjusted as it moves through, because of the spins that it sees in the skyrmion local spin structure. And this in effect is the same as the Lorentz force that it would feel in the presence of a magnetic field. So this in effect is something that can be used to control the skyrmion. So you can actually rotate the skyrmions and move the skyrmions using electric controls, and these have been measured experimentally. So the other way of looking at this is for it to be very similar to magnetic domain wall movements. So we are all familiar with magnetic domain walls and how they can be moved for magnetic recording purposes. Now the skyrmions are also quite labile, and they can be made to move. And it turns out that you need to spend much less energy to rotate a skyrmion in comparison to the magnetic domain wall. So in effect, what this was proposed by Fert in this paper here, and these people here, they actually calculated that to rotate the skyrmion lattice, you just need this much energy. So together, these predictions actually point to a much greater possibility for using these materials, very similar to how you would use the magnetic domain wall movements. So what are the materials that are commonly being studied? So this is a list of materials that have been studied so far, some of which have been studied only in the last about 3 years or so, of which these two fall under that category, and these are quite well investigated. So one of the characteristics is that they all lack a center of inversion, because you need the Jalashinsky-Moriya interaction to be effective, and they all form in either chiral space groups or polar space groups as in this. This was a more recent discovery. And this is the temperature range in which the skyrmion lattice exists. So if you have a look here, the cobalt, zinc, manganese is really interesting because you can stabilize them at room temperature, as is the iron germanium, whereas these are at much lower temperatures. And there is no need for them to be insulating, they can be metals as well. So these are the different types of materials, and this slide here shows you what the structures are of these materials. So you've got these chiral space groups. This can I'll show you a bit more about this. And then you've got this magnetoelectric material, which has been very well studied for its magnetoelectric properties, and then the manganese silicide as well. So these are the really well studied materials. The material that was first studied for its skyrmion behavior is manganese silicide, and that is a cubic chiral lattice. Okay. So it shows helical ordering, and you'll often see, when you see the skyrmion phase diagram, this A phase here. So what it is that with the magnetization measurements, you can map out a small region here in field and temperature where the skyrmion phase really exists. So if you like, the helical ordering is almost like a screw-like ordering of the spins, and you need a special helical ordering for the skyrmion phase to exist. And if you remember, I said that the skyrmions exist as a lattice in the structure. So you can view this in a very similar way to how you would view the vortex lattice in a superconductor in the superconducting state, where you have vortices spaced in a superconductor. And this is very, very similar. So you could use diffraction techniques. Here they've used a small angle neutron scattering technique, which is very effective in mapping the vortex lattice in superconductors. So the very same technique has been used here with the fields necessary to stabilize the skyrmion phase here. So as long as you're in the right temperature range, in the right field range, you can map the skyrmion phase, the skyrmion lattice, using small angle neutron scattering. And that shows the helical or hexagonal ordering of the skyrmion phase in manganese silicide. So this was conclusive proof that the skyrmions exist in manganese silicide. So once again, I've given you a range of materials that exhibit these skyrmions. This shows the temperature range. This shows the modulation length of the skyrmions. And skyrmions can have also been seen at the interfaces of ferromagnets and heavy metals. And these are all the systems that have been investigated to date. Now this bottom part here shows you what techniques are effective in mapping these skyrmions. So if you take the bulk and the films of materials, as well as the bulk here, in the bulk, the most effective technique in reciprocal space is the neutron small angle neutron scattering. You can also do X-ray studies, and Lorentz TEM measurements are also very, very effective. You can actually map. Yeah.
The last one is the
Yeah.
no magnetic.
It is magnetic. Yeah, I'll show you a bit more about it. Yeah, it is. Yeah. So Lorentz TEM is another method with which you can actually view the skyrmions, and it's a very powerful technique. So you can also have MFM microscopy techniques, and then STM as well. So in our team, we have people who can do neutrons, X-rays, as well as Lorentz TEM measurements, and we have access to people who have these techniques as their specialty as well. So at Warwick, what can we do? So we are tasked with producing these materials in the best form that we can. We are also tasked with trying to extend the system of materials that exhibit these skyrmions. So we can synthesize both polycrystalline and single crystal materials by a range of techniques. We use the optical floating zone technique very widely for many materials, and some of the materials here lend themselves to crystal growth by these techniques. We can also synthesize metallic materials by arc melting these and by attempting to produce crystals by the Czochralski technique. But by far the most effective technique that we find is suitable for a lot of these materials is the chemical vapor transport technique. And this we have used in the past for growing single crystals of various layered dichalcogenides. Now there's a big business in these materials. Ever since the discovery of graphene, there's been a lot of interest in these layered materials. So the same techniques can be used to grow materials that exhibit skyrmions as well. So what we do here is that we take the material that we want to grow a single crystal of and mix it with a transport agent, and then we just put it at a temperature gradient between the material end and where we want the crystals to be transported. And after a long wait of a few weeks, 2 to 3 weeks typically, we can get crystals of these materials. So this here shows you the size and shape of some of the crystals that we can obtain. I mean, these may be very small compared to many of the other crystals that it is possible to grow, but they are sufficient for most of the studies that we wish to do with these crystals. So that's typical of these copper oxyselenate crystals. So what they look like is in a tube, they just form, you get a good harvest of these crystals. Now it's very important to determine the actual space group of the crystals that you produce, because that is key to whether the material can host skyrmions or not. It has to be this big square there is 1 centimeter. So they are at the most about 8 millimeters across, but they come in a very well-formed morphology. So it's very critical to establish the space group. So you need to do single crystal diffraction, X-ray diffraction, to determine the space group, as a very close relative of this material can also form in this process, so you cannot afford to confuse the two. So this shows ferrimagnetic ordering around 57 to 58 Kelvin. Okay. So if you measure the susceptibility as a function of temperature, you see a very sharp transition at the ferrimagnetic ordering temperature. And Shinichiro Seki has mapped the phase diagram of this system thoroughly, and we know exactly where to look for skyrmions in this system in terms of temperature and magnetic field. So we sit at that particular phase, which is the A phase that I told you about, which is mapped here. So it's a very small temperature interval here, and you need to be between 200 and 400 oersteds, and you'll be able to map the skyrmion phase, which is what we've done with our crystals. So at Cambridge, for the Lorentz TEM measurements, these crystals are actually thinned down. Very thin sections of these crystals are taken, and if you sit at the right temperature and the field, you can actually see the skyrmion. So this is there are various videos available in the literature of how people have actually imaged the skyrmions. It's quite now it's quite a well-established technique, but it's a technique which involves applying a magnetic field gradient and then going in focus and out of focus periodically to try and image these skyrmions. So what you can also do is you can move these skyrmions in a magnetic field gradient and photograph them as they move in a magnetic field. So you can play a lot of games with trying to understand this and trying to get at the actual dynamics of the skyrmions in each system. So for those of you who are interested, yeah? Yeah, they are. So the observation of skyrmion, the stability of the skyrmion lattice in a sample could be affected by disorder and so on. So there's still not enough knowledge about how these parameters would affect the skyrmion lattice. But if you've got the right space group, and if you've got the right crystal structure, and if you prepare your specimens, I mean, obviously there are some techniques which the microscopists know, to employ to get the best out of their samples. So it is possible to image them quite easily, I gather. Okay, but you have to be on at the right temperature and field, and also be an expert at how to get the best out of your TEM, I expect. Yeah. But we still don't know how sensitive the skyrmions are to disorder and grain boundaries and so many other aspects. So the other thing that we are trying to do as part of this project, the people in Durham, especially Dr. Tom Lancaster, is an expert in the use of muon spin rotation. Now muons can actually go and sit in a specific site in a crystal, and they can sense the local magnetic field. So they are a very microscopic, a very good microscopic probe to use. So what he has done is to take these samples. You don't need a crystal, you can just work with polycrystalline material, and you do a transverse field muon spin rotation experiment. So basically you're looking at the output signal of the muon spin rotation as a function of field by staying at the temperature at which you can observe the skyrmion. So he's gone all the way from 60, which is above the ordering temperature, to 54, which is just below where the skyrmion face is seen here. So at 54 you wouldn't see the face, and at 60 you wouldn't see the face here. So you see it between this narrow temperature region here, and you can pick up the presence or absence of the skyrmion by the anisotropic shape of the response of the muon spin rotation. So he's developing this technique to be able to map the skyrmion face in materials, and he's done this both in bulk crystals as well as in thin films of manganese silicide. And we will be applying these to systems where we don't know yet what the extent of the skyrmion phase is. We can just use this signal to tell us where the skyrmion phase arises and where it disappears. Okay. So I said one of our aims is to try and expand the range of materials that exhibit skyrmions, and one way of doing that is to just tinker with the actual crystal structure. Now in the copper oxyselenate there are two different copper sites, and depending on the substitutions at the two different copper sites, we expect changes in their physical properties as well. So one of the favorable substituents is zinc, and it's not yet known where the zinc actually goes in these copper oxyselenate crystals, and we'll be doing experiments to try and ascertain that. And what's interesting by substituting zinc at the copper site is that it's been reported that you can have two different pockets where the skyrmions are seen. If you remember, I showed you just one pocket in the pure material. There are two different pockets predicted in these zinc doped samples. So what we have done is that we've produced crystals of these zinc doped materials, and we've done experiments both on powder and single crystals to see how the transition temperature, the magnetic transition temperature changes as a function of zinc concentration in these materials, and also mapped out the skyrmion phase both in the polycrystalline material and the single crystal material. So the way we arrive at these plots is either to sit at temperature and scan the magnetic field and look at the AC susceptibility response, and then you can see the anomalies in the AC susceptibility response directly, which indicate these pockets, small pockets here, which show you the skyrmion phase. So ideally, we want to be able to expand the temperature region in which you can observe the skyrmion. So it's not just centered around a very narrow band in temperature and in field. So the other example that I told you about is this cobalt zinc manganese alloys, where the excitement is due to the fact that you can observe skyrmions close to room temperature. Okay, so these can form in a whole range of compositions. So you can have a whole series of compositions, and we are investigating most of the members of this series to see which materials are most suitable in terms of a stable skyrmion lattice. So we can produce reasonably sized crystals of the cobalt zinc manganese material, and these are grown by the Bridgman method in our lab. And of course, the range of temperatures at which they undergo the magnetic transition is key. So you need to know exactly what temperature to be at. And this is a previous study of the small angle neutron scattering, similarly imaging the skyrmion lattice in these materials. So coming to the gallium vanadium for sulfurate, now they do, so they are a polar crystal lattice, and this is an interesting class of spinel compounds which are called the lacuna spinel, because in the crystal lattice there is one gallium atom missing, for that is every other gallium atom is a void. So it's called the lacunar spinel structure. And these are a very interesting class of compounds. They don't just exist for the gallium, vanadium for sulfurate. You can have various substitutions for the vanadium and the gallium in these as well. So they undergo a magnetic transition at 13 Kelvin, and they are seen to exhibit the skyrmion phase over a wide temperature range. This is from 18 to 13 Kelvin, unlike in the copper oxyselenate where you just had a 2 Kelvin interval where the skyrmions are seen. So we are looking at the entire phase diagram going from the sulfurate to the seleniumate, and here again crystals are produced by the vapor transport, but they are really minute here, and we are working on trying to get larger crystals. But these, they are not, I mean, they are still usable. We can form mosaics of these crystals for a number of the experiments that we want to do. For a lot of the X-ray work, these are more than sufficient. So the sulfurate member has been very well studied and been reported. So the skyrmion phase is very well reported in those. And we are trying to look at intermediate phases. And we think that the seleniumate material, which also orders ferromagnetically below 18 Kelvin, is a very promising candidate for. Okay, so this is the one, the red one. The red is the skyrmions here. Okay, so there is a relatively wide temperature range compared to the other materials. So our aim is to try and get more materials and study how they exhibit. So there are two more materials that we hope to be able to have samples of that we can investigate, and this is a material which is a part of the Heusler alloy family, and the Heusler alloys are a huge family of materials that exhibit a variety of properties. And now there are a lot of problems associated with these materials, although skyrmions have been known to be present in these materials. They undergo a phase transition very close to room temperature, and the skyrmions are actually confined to in the twin boundaries that are seen in these materials, which is what is reported. So we are trying to produce large crystals of these and try and investigate the skyrmions in these and try and understand the dynamics of skyrmions in these materials. The same with this material here. I won't go into more details about this because it's all quite speculative, and the reports are of a biskyrmion. So a biskyrmion is just two skyrmions joined together like a molecule. So these are all the materials that we are working on, and we hope to be able to make some breakthroughs in our understanding of at least the existing materials, if not newer materials. So I'll end here and summarize, saying that the skyrmions and the skyrmion lattices have been observed in a whole variety of materials. I've tried to show you a few of the interesting classes of these. They can extend in size to several nanometers, and I think what the applied physicists are more excited about is the possibility of exploiting some of these unique properties that the skyrmions exhibit. So I'll thank you for your attention and stop here.
Microphone's okay, better? Yes, I have the first question actually. Is about the physics of